let's actually do a just on your own exercise for a moment. This is cyclohexane. It's not benzene. If you were to treat this with Cl2 and UV light, how many unique products would you get? Draw them all. What if we did the same thing with Br2, UV light? How many unique products would we get from cyclohexane? Again, you'll first have to look at cyclohexane and identify all the hydrogens and figure out, are they all the same? Are they all the different? Or are they many differences? Or are they all different? There's actually 12 hydrogens on this molecule. Should we draw 12 products here? I sure hope not. So draw the products you think we should have here and here. How many? What their structure is. Do the same thing for bromine. Just keep working on the first one. Right? I'm hopeful for this particular one that you got one product. Okay? I'm hopeful that you simply just drew chlorocyclohexane. Or if you drew it with a wedge or a dash, these are all actually equivalent. This one looks not so good today. But if you drew it with a wedge, dash, wedge, or straight, these are all exactly identical. There's no other possible product. You know that chairs can flip, interconvert, or ring flip from axial to equatorial. You know all about that, but those aren't unique products. If you had actually drawn this as a chair, put chlorine up, well, it can ring flip. Maybe you drew it as a chair and drew chlorine equatorial. All the things I'm drawing here, and my sketches aren't very good, it's fine, because the point is there's only one possible product for the radical chlorination, the monochlorination of cyclohexane. These compounds are all called chlorocyclohexane. If we drew the chlorine up, same as if we draw it to the right. Okay, if you had trouble with that, then do the same one for bromination. How many unique products there should be? If you had more than one as your answer, fix it now and correct it. Think about why you got it wrong. Still, also only one possible product for the radical bromination of cyclohexane, and that's bromocyclohexane. We're going to switch it now. We're going to switch it for this, and this might turn into be a disaster, but I'm going to ask a few people to put their answers for how many unique products we get for the radical chlorination into the chat. Now, I don't want 39 people to write their answers in, right? And if you're really shy and you want to just send it to me privately, by all means, I won't single anyone out. This is a learning experience. I wanted you to think how many unique products there are for the radical chlorination of methyl cyclohexane. This methyl group changes lots of things now. There's no longer the same level of symmetry we had in this molecule. This particular molecule has symmetry everywhere. It could cut it that way, cut it that way, cut it that way. Every single CH2 group is the same, and the CH that's up or down, those are also the same. And we only can get one product from it. But now, there's not much symmetry in this particular molecule. There might be a little bit, but the total number of hydrogens in this are 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We don't have 14 products here, but we definitely have more than one. Try and sketch a few of them. I'm leaving some open time here, a few minutes. Just sketch, doodle, and try and draw in unique products. If you can, try and name them casually in your mind, like 1-methyl-2-chloro cyclohexane, or 1-methyl-3-chloro, or cis 1-methyl-2-chloro cyclohexane. Just sketch out and draw. Think about all the different products you could get here. There's a lot. There's less than 12. Thanks for sharing one answer here, 3. We're on the right track. We're getting warmer. It's better than 1. When anyone wants to share an answer, please go for it. Just type a number in the box. Again, if we were in class together, I'd probably ask you to speak up and tell me about this. Actually, the person who answered 3, if you want, unmute your mic and maybe you can talk me through and tell me where you think the answers are. If you don't want to talk, Don't unmute your mic. It's absolutely fine. But if you do, you can kind of tell me, we can kind of point at these together, and you can tell me where the 3 products you think there are. Up to you. 5, we're getting warmer. Well, it's good. We have a couple here. 6, 3, 3 and 3. Nice. Okay. Well, we're going to do some of them here. Actually, there's quite a few products here, and for this first one, and I'm not going to actually draw them all. But what I'm going to do is I'm going to redraw this molecule just slightly larger. And I'm going to draw in some dashes and wedges. And we're going to do a thought exercise together. Because 3, that's a good answer. 5, not a bad answer. I'm glad and appreciate those things that you filled in. So this molecule is drawn out a little bit differently. I'm kind of omitting the ones over here because technically this molecule does have a plane of symmetry. Things on the left and the things on the right of it technically are the same. There's a hydrogen over here and up. There's a hydrogen over here and down. Those are the same as these two. There's a hydrogen up here. There's a hydrogen up here. That's the same. There's a hydrogen down here, a hydrogen down here. These are the same for all intents and purposes right now. But I think this is unique. You tired of me hearing me say that word? It wasn't fun to say. This is a primary position. If we put 1 chlorine here, that would be a unique product for sure. Hopefully some of you guys did that. Hopefully some of you put a chlorine off of here. Right here is a tertiary position. This hydrogen is definitely different than that one. If we drew a molecule here, chlorine would be coming off, and if we drew a molecule here, chlorine would be at this tertiary position. So there's 1 product for this methyl group. There's a new type of hydrogen here. That would give a new product. So we're up to 2. What if we put chlorine here at this position? If we put chlorine here, it'd be called like 1-chloromethyl-cyclohexane. If we put chlorine here, it would be called 1-chloro-1-methyl-cyclohexane. If we put chlorine here, let's just call it the 2 position. All right, let's just call this 1. Let's just call this 2. We would have 1-methyl-2-chloro-cyclohexane. What if we put the chlorine group down here? It would be a 1-methyl-2-chloro, but is this position and this position the same when we have a ring? Think of the words cis and trans. If chlorine's up and methyl group's up, we would call those cis. If methyl group's up and chlorine's down, we would call that trans. These 2 positions here are not the same. So we're up to 4. 1 here, 1 at the tertiary position. At this second position, it's a secondary carbon. We call this carbon number 1, 2, 3, and 4. We could have up-down isomers. Now we're at the 3rd position out here. If we put chlorine here, is it the same as if we put it here? No, it's different. This would be 3-chloro-1-methyl or 1-methyl-3-chloro. If we put it up, cis, down, trans. 2 more products. Now we're at the 4th position. We're exact opposite side of the ring. What if we put chlorine here? What if we put chlorine here? Well, this would be something like 1-methyl-4-chloro. And if they're both up, it'd be cis. If the chlorine's down, it'd be something like 1-methyl-4-chloro, and it'd be trans. So there's 2 more products. This particular molecule gives rise to 8 products. And I'm glad that people wrote in numbers like 3, 5, and 6. I'm glad no one wrote 1 and no one wrote 22. I'm happy if it's somewhere in between those 2 numbers. I'm very forgiving in lecture together. Okay, so chlorine is very indiscriminate. It's very reactive. It would go to all these positions. We're not going to figure out what's the yield, what's the major product. Those things don't matter, just how many products we could make. Now, based on our previous discussion about bromine, I want you to think of this idea that we just talked about bromine, that bromine really is honing in on a very particular type of carbon. one that's highly substituted,